So let's talk sound. You've been listening to me, so let's talk about how this works. So sound is going to require a medium to move through because it's a longitudinal wave, as I talked about in a previous video. It requires something that has particles to push together and spread apart in order to move. So that means there's no sound in a vacuum. Sound does not travel in space. So it is true. No one can hear you scream in space. Unless you have a microphone, but you know. So how does sound travel as far as speed goes in different materials then? Because longitudinal waves, as I talked about in a previous video, can move through solids, liquids, and gases. Well, in air, about 20 degrees Celsius, that's just kind of normal room temperature. The speed of the speed of sound is about 340 meters per second. So we usually use somewhere around 330, 340 meters per second for the speed of sound. Mostly because when we are dealing with sound, we're mostly using it as far as the speed of sound in air. In water, the speed of sound is about 4 times that. So 4 times 340, so, over 1,200 meters per second. And then if it's traveling through something like steel, we're talking about 15 times the speed of sound in air. So a lot faster. So the question is, why does this happen? Why is sound so much faster in a solid like steel than it is in air? Because to us that kind of doesn't make sense, mostly because we mainly listen to sound in the air. But if you think about it, you may have heard of if you want to listen for a train, you should put your ear on the tracks and you'll hear it first. So what is going on? Well, let's look back at the slide picture from the slide from a previous lecture on states of matter. So here we've got our solid, our liquid, and our gas. And sound is a vibration, a wave that has to move through matter, which means it has to be moved from one atom to the next. And if you look, in a solid like steel, those atoms are pretty close together. And so it won't take very much time for that wave to go from here to here to here and so on. And so that's why in something like steel, the sound waves can travel pretty quickly because the atoms are very close together. Versus something like liquids where they're a little farther apart. And so the waves have to travel a little farther in order to be able to pass that vibration. And then in air, it's even farther. And so there's a lot more distance to travel. And remember, in gases, those particles are moving a lot faster. And so they are basically having to chase each other in order to transfer that vibration. And so that's why there's that big difference in speed, because those molecules and atoms are much closer together in a solid than they are in a liquid or a gas. All right, so one of the properties I want to look at for sound is what we call interference. Now, this is where you get an effect of 2 or more waves overlapping. Okay, and so you can actually see they've done a sketch of that here, what that would look like. But here, this is actually interference with water waves. So they've done 2 disturbances right next to each other, and you can see that those waves are interfering with each other and making the waves not nearly as distinct. This is a property of all types of wave motion. So we actually see interference in both light and in sound. But I want to focus first on sound. So there are 2 types of interference. The first one is what we call constructive interference. So here what we get is the crest of one wave overlapping the crest of another wave. So if we look down here at the bottom, so we've got our waves, and they line up together. They happen at the same time so that the two waves fit together. And instead of having two smaller waves, you get one bigger wave. And with amplitude and sound, amplitude is related to the loudness of a sound. And so when you get constructive interference, this reinforcement makes the sound louder. Okay? So you can get a louder sound when this occurs. Destructive interference, on the other hand, happens when the crest of one wave overlaps the trough of another. So you can see that here. So we've got the crest here, the trough here. When these two come together, they end up canceling each other out. If they're identical, they will completely cancel each other out. If they are close to each other but not identical in amplitude, they will reduce the amplitude and quiet that sound down. So where does this sort of thing happen in the real world? Well, if any of you have noise canceling or anti-noise headphones, this is how they work. It's actually really cool when you think about it. Most people don't realize this is why noise canceling headphones are bigger than regular headphones. It's because they actually have two sets of speakers. So you have this set of speakers that are pointed towards your ears to be able to play the music or whatever it is you're listening to. And then the other set of speakers are pointing outwards. And they're connected to a little microphone with electronics. And that little microphone is listening for any incoming sounds. So it's measuring the sound in amplitude and the frequency of the incoming sounds so that the speaker in your headphones can match that frequency and amplitude and send it out. So that when they run into each other, you can see here's the external, the orange, and the one that your headphones send out is the red. They will cancel each other out and create silence right around your headphones. So this is how those anti-noise or noise canceling headphones work. You've got that second speaker pointed outward, making basically sound, but you just can't hear it because it's being canceled out by the sound that's around your headphones. So the next one, oh, my face is over top of them, is the Doppler effect. And this is related to sound. But this one is kind of interesting because this one has to do with sound and motion. So the Doppler effect is a change in the frequency of sound waves as measured by an observer due to motion. So the motion of what? Well, it's the motion of either the source of the sound or of the listener. So either one can move, and that changes the frequency of the sound waves. So let's take a look at what we're talking about. So over here, we've got a diagram of our sound waves. So here is the noisemaker right in the middle. So it's emitting the sound. And so the sound waves are going out. And each of these little wave or sound fronts are showing you the frequency. So the frequency is the space between the circles or wave fronts. And so as these are going out, we've got the same frequency going either way. And so it's going to sound just like what we expect. But if you move or the sound moves, it's going to change. And something I forgot to mention when I talked about frequency in my previous video is that frequency is tied to the pitch of a sound. So how high or low a sound is to sound to us is related to the pitch. So the higher the frequency, the higher sound of pitch it has. The lower the frequency, the lower pitch sound it has. So if we look here, if the motion of the object goes towards the observer, it squishes those sound fronts. It squishes the sound waves, which means that the frequency increases. Since the frequency increases, that means that it's going to go higher. The sound will go higher. For if you're standing on the other side and it's going away from you, those waves are going to space out and the frequency is going to go down. And so the pitch of it will go down. So this does happen for all waves, from sound to light, but the one that we're most familiar with for the Doppler effect is sound. So can you think of any examples? Think about things in your life that you hear that when they go by, they change how they sound. And if you're thinking of things like fire engines and police cars, those are the most common things that we have that do this. So as a fire engine or a police car comes toward you, it gets it starts to sound louder and higher pitched. It gets more irritating, and then as it passes you and starts to go away, it seems to start getting quieter and lower pitched, less irritating. That's the Doppler effect. All right, and I've got a video here. You should
speed it up once, then slow it down, bring it to rest so we can hear the sound that it's emitting. Beautiful.
So hopefully you can hear that. He's standing in what we call an anechoic chamber, which means that there are these baffles that are soaking up the sound, so we can hear just the thing that he's swinging around. So it's the same sort of thing as that device swings towards you. The pitch is going to change as it swings towards you and away from you, towards you and away from you. And as you probably noticed, once he stopped and pointed it at you, the pitch changed completely, because now all of the sound waves were coming at you at an equal frequency. Oop, stop. So here we go with the Doppler effect. Like I said, fire engines, ambulances, anything that has one of those kinds of sirens on it is going to create the Doppler effect as far as sound goes. So another property related to sound is the reflection of sound. So the reflection of sound is just waves of sound rebounding off of surfaces. So you've noticed this all of your life. You just probably didn't realize that's what was happening. So you can see over here, we've got a sound source, and those sound waves are going out and bouncing off of the walls. And some of those sounds are making it to the observer. Some of them will keep bouncing and then eventually make it back to the observer. Some of them will never make it back to that observer in the room. And the thing is that the reflection of the sound is going to be determined by the nature of the material. So think about hard surfaces and smooth surfaces versus soft and bumpy surfaces. So I'm sure you've been in rooms where all of the surfaces are hard and smooth, like concrete, wood, so forth. Think like a gymnasium. And think about what the sound is like in there. It's generally very loud, right? Even if there aren't very many people there. And that's because there's a large amount of reflection of sound going on. The waves are hitting and bouncing back off of the different surfaces. Versus something that's soft and bumpy. Think of some place that has lots of soft furniture, carpeting, and so forth. And that's because the opposite is happening. The sound waves are going, hitting those soft surfaces, and often being absorbed or bounced in a direction that never makes it back to you. And so think about things like libraries, right? Libraries are not usually made out of things like concrete and wood. They're covered in soft surfaces. So I've got a couple of videos to show this reverberation. This occurs in different areas because of this reflection. It's a mixing of reflected sounds because of these hard and smooth surfaces versus soft and bumpy. So I've got one for a balloon and one for a saxophone. What they're going to do first is they're going to, in each video, show you the balloon pop or the saxophone in a room that has hard and smooth surfaces. And that will show you the reverberation, and then you'll be able to see, well, not see, hear what it sounds like when they're in a soft and bumpy room, because you can see in these pictures here that they've got these big shapes behind them. Those are anechoic chambers again. Those are soundproof type rooms. These are recording type studios. So let's do the saxophone first. So you can hear kind of like vibration. And it's a very different sound when she's in the recording studio. You can tell when she turned around, you couldn't hear her as well because the sound waves were pointed away from you. When she turned back around, you could hear her better because they were pointed back at you. The reason why a lot of artists record in those studios is because it reduces or removes that reverberation, that vibration type sound that you hear. The thing is that we're so used to reverberation that when we hear things without it, they sound odd. So let me play you the balloon pop with reverberation and without. And this will show you what I mean. Sounds normal, right? Now let's hear it in an anechoic chamber. So very different. And like I said, we're used to hearing reverberation. We're used to hearing those sound waves bounce back at us.